All right, we are talking about Gibbs Free Energy today, and hopefully by the end of this video, understand this classic example that illustrates this concept called Gibbs Free Energy. But before we go there, we need to know and understand these two concepts of enthalpy and entropy, because it's these two concepts that will define our definition of whether or not a reaction is spontaneous or non-spontaneous, whether it's going to just happen or if you're going to need to constantly add energy to it to keep going. So first concept is this, enthalpy, H. And you've heard of this before. This is probably your first introduction into spontaneous and non-spontaneous reactions, was this concept of exothermic versus endothermic. And you probably learned about it like this, where you would look at a reaction and you would see the reactants and the potential energy in those reactants. And then you look at the products and look at the potential energy stored in the bonds of those products. You would look at the potential energy of the products compared to the reactants. And if the products had a higher potential energy stored within them, that would indicate that energy was absorbed in this reaction. And we could then say that this was an endothermic reaction. And we would say that delta H in this case was positive. The change in enthalpy was positive. On the other hand, if we looked at the potential energy stored in the reactants and products and compared those two, and we noticed that the overall energy of the products was lower compared to the reactants, then we would say that the energy was released, and this would be an indication of an exothermic reaction. And we would say that the delta H was negative. And we see this. The classic example was, lighting of the match. Once that match has been struck, that's the activation energy. But once that activation energy has been met, that reaction just continues spontaneously. You don't need to keep adding energy to it. The reaction will go until it is complete. That was a classic example of this exothermic reaction. And that was where we got introduced to this concept of spontaneous and non-spontaneous reactions. However, we need to consider this. It's the second concept. It's called entropy. Entropy might be something new to you. This is the degree of disorder or randomness in a system. Now, this is reflected in the second law of thermodynamics that states that disorder or randomness in the universe is always increasing. That's the natural tendency of our universe, is that we tend towards randomness. In this example, we have something that's highly ordered or structured. It's the natural tendency for it to simply break down into smaller components, increasing the randomness. This is a very spontaneous type of reaction. It just happens. One example that I give, a hot cup of water will just naturally cool down. That particles that we have here are going to naturally want to move outward and release their energy into the surrounding environments through random collisions. That's this driving factor called entropy. And we understand this intrinsically because we would think it would be very odd to have a cup of water on a table and just have it spontaneously become hot on its own. So this is what we refer to as entropy. And we could describe it as this S. In this case, when we go from something that's very organized into something that's more random, or we've increased the randomness of it, we would say that the delta S is positive. Now, it does go the other way too. If I take something and I decrease the randomness of it, like this, we would call that decreasing randomness. We would say that this is a very non-spontaneous type of scenario. We would need to have energy added in order to make this happen. And we would say that the delta S in this case is negative. So with those two concepts in place, we can now address this question of how we can tell if a reaction or process is spontaneous or non-spontaneous. Because we now need to consider enthalpy, whether it's exothermic or endothermic, and we relate that to delta H, as well as now entropy. Is what we are getting becoming more random or less random? We would capture this as delta S. This is Gibbs Free Energy. Gibbs Free Energy does this. It factors in those two concepts, enthalpy and entropy, and you will see it as this equation here. When it comes to Gibbs Free Energy, which we would say is G, if we want to determine whether or not a reaction is spontaneous or non-spontaneous, we would have to calculate the delta G, the change in Gibbs Free Energy. Now, a negative change in Gibbs Free Energy, meaning that we have a delta G that's less than 0, would indicate a spontaneous reaction, and we would call this exergonic. This is the new term now that I want my students to understand, that we're not talking about exothermic anymore. That is for enthalpy. this new term that we need to now understand when it comes to whether or not a reaction or process is spontaneous or not is it exergonic or is it endergonic? And in the case of endergonic, it's a positive change in Gibbs free energy where the delta G is greater than 0. And this is a non-spontaneous type of reaction or process. All right, so let's take a look at this equation. What it's telling us here is this. There's our delta H. This is our change in enthalpy. And we're going to subtract our change in entropy multiplied by the temperature. And overall, whatever change we get, whatever value we get, if that value is negative or a negative delta G, we would say that that is exergonic or spontaneous. If the delta G is positive, that would be a non-spontaneous or endergonic type of reaction. Let's play around with this equation, and we are going to, at least for right now, let's just ignore the T, the temperature right now. Let's just work with these two concepts that we've just talked about, the change in enthalpy and the change in entropy there. And what we're going to do is let's talk about this in terms of a scenario. So here we have scenario 1. If we had a reaction or some sort of process that released energy and the particles involved in the reaction became more random at the end of it, could we determine whether or not this reaction is spontaneous or not based on Gibbs free energy? So in this case, well, because it is releasing energy, we would say that that is an exothermic. And we said that exothermic is a delta H that is negative. So I'm going to put a negative there. So whatever value it is, this value is negative. And we're not going to worry about numbers right now. The other thing was, okay, let's take a look at the delta S, or the change in entropy. And because in this reaction, the particles are getting more random, we would then express that delta S as positive. Again, I'm not going to get into specific values here, but the overall value, whatever it is going to be positive because it is becoming more random. Then, as we do the calculations, based on what we know and remember from math, if I take a negative value and I subtract a positive value from that, I'm going to end up with a negative value. So overall, we could then say that the delta G is going to be negative. And that would mean that this would be an exergonic type of reaction. And it would be spontaneous. Now, hopefully this makes sense, because if we have something that is exothermic, we understand that as being spontaneous. And if we also, in that same reaction, have something that is becoming more random, that is also spontaneous. So together, it only makes sense that, yes, this would be a spontaneous reaction. Let's give you another scenario here. Let's say we had a reaction that absorbed energy, and the particles involved in the reaction became less random. So taking a look at this equation, our delta H in this case would be positive because it is endothermic. The delta S would be expressed as a negative value because it is becoming less random. When it comes to completing our calculation here, again, irregardless of the values, we would know that if we took a positive value and subtract a negative value from that, we're going to end up with a positive value. So in this case, delta G is positive. That would make delta G endergonic, non-spontaneous. And that should make sense because endothermic reactions are non-spontaneous. Reactions that involve the particles becoming less random or more organized is also non-spontaneous. So overall, the reaction should be non-spontaneous. All right, you might be seeing where this is going now. Let me give you a third scenario. If we had a reaction that absorbed more energy from the environment and the particles involved in the reaction became more random, what would Gibbs free energy say about this? So because we are absorbing energy, we would say that the delta H is positive. It is endothermic. And in this case, because we are becoming more random, our delta S would be expressed as positive. So what would the value be for delta G? Up until now, we've been able to get away with not using values. Well, here we would now need to know the values, because taking a positive value and subtracting another positive value, it could result in an answer that is either negative or positive. And it would depend upon the values that we would have in these two places here, our delta S and our delta H. So in this case, if we had a very large delta H here that was very positive, and we subtracted a delta S from it that was not as large, we would have an overall positive value here. Now, since we're talking about energy here, the values that we'll be using are in joules. So if I were to give you a value of, let's say, delta H is 10 and our delta S was 5, I would take 10, subtract 5, it would still be positive. It would be positive 5 as our delta G. So as a result, this would be an endergonic type of reaction here, or non-spontaneous. However, if I had a delta H of a certain value and the delta S was much larger than that, let's say I had a 10 here for my delta H and a 20 here for my delta S, we would end up with a value that would be negative for our delta G and result in a reaction that was spontaneous or exergonic. So for this particular scenario, it really depends now on the values. But that gets us into this topic where we can now understand how Gibbs Free Energy explains how the cold pack works. Now, if you're not familiar with these, releasing the contents inside of these cold packs causes the cold pack to get cold. So the cold pack gets colder, and it is a spontaneous type of reaction that you're seeing here because it just continues to get cold. Looking at Gibbs Free Energy, if we were to look at the enthalpy of this, it's getting colder. We are not releasing energy here in the form of heat. We are actually getting colder. So our delta H would take on a positive value. It would be endothermic, and it would not be spontaneous. And yet, the ice pack continues to get colder and colder and colder. So what's driving this? Can't be enthalpy. We could explain it looking at the randomness or the entropy of the particles inside of this cold pack. In fact, the change in the entropy is so large, meaning that it has a very large positive value, that it actually drives this reaction. This overly large positive value gets subtracted from the enthalpy here, or the change in enthalpy, and we end up with a negative delta G. That makes this spontaneous or exergonic. So in this case, yes, it is the large increase of entropy inside of these cold packs as those two substances mix together that drives this reaction and makes this spontaneous, even though it is not releasing any energy into the environment. In fact, it's getting colder. It's what's happening here with the entropy that is making this reaction happen. So I got to bring this up now. We've been ignoring T up until this point. So let's look at T, temperature, measured in Kelvin. Now, we need to factor this in because temperature, if you remember, it's about kinetic energy. Temperature is the measurement of kinetic energy of particles. So this does impact the randomness of substances. It can help increase or decrease the randomness of particles in a substance. And this goes back to what you learned way, way back earlier in science. You know, in lower temperatures, particles would tend to move less. That is really part of this randomness that we're talking about here. And as we increase the temperature, well, those particles tend to move around more. That increases the likelihood of randomness. That's why we have temperature here, because we need to factor this in because it does impact just how random the particles are going to be in any given substance, in any given reaction. Let's review this. So if we have a change in enthalpy that is negative or exothermic, and a change in entropy that is more random or positive, we would have a delta G that would be negative or spontaneous overall. However, if we had a delta H or change in enthalpy that was endothermic or positive, and a delta S or a change in entropy that was negative, or meaning that we were becoming less random, we would have an overall delta G that was not spontaneous or positive. Now, for the next two scenarios, they're going to be really dependent upon the values here. Because if I had something that was overly endothermic or a delta H that was positive, as well as a change in entropy that was positive, meaning that we were becoming more random, it would depend on which one was larger that would determine the overall delta G value. It could either be negative or positive. Similarly, if we were to look at something where we had a delta H that was exothermic or a delta H that was negative, as well as a decrease in the randomness of those particles, we would have to determine the values of these two values here in order to calculate whether or not the overall delta G was negative or positive. So there it is. I hope that this helps. Again, I'm going at this from a biology perspective because this is underlying many of the processes behind stuff like metabolism, or the reason why we have concentration gradients or electrochemical gradients and how they work, coupled reactions. All of these things really involve not just whether or not something is exothermic or endothermic, but really also the move towards randomness or becoming less random and requiring the input of energy to make stuff like glucose or to create proteins. All of these things are present in biology and they involve Gibbs free energy. All right, I hope that helps. Good luck to you all. Talk to you later.